Hi, my name's Andrew McLaren. Today we're going to be going over vectors and how you can use that with reference frames to solve problems where you maybe have motion relative within a reference frame and outside of that reference frame, and you're trying to figure that out. There's a lot of things online about this, and there's like different formulas. Sometimes you're adding two velocities, sometimes you're subtracting them. It can be a bit confusing. And so we're going to go over some tips for that. My number one would be use simple numbers in place of these more complicated numbers just to kind of test your understanding. We'll go over that with an example problem and a couple other like simple scenarios. And then we're going to look at a one-dimensional problem, and then we're going to look at these two different two-dimensional problems. And that should be all what we're doing in the video, but it should help you with your problems as well, because that's really the most complicated thing, and this is just kind of trying to figure out what's going on in one dimension and then how to think about it in two as well. So if we're looking at the problem here above, there's some complicated conversions that you're having to do. So we're going to just try and make this as simple as possible. If we look at some velocities, this could be the bird relative to the earth, the bird relative to the air, and the air relative to earth. Those are the notations that they'll usually give. It's like this relative to that as the subscripts. And that can help you a lot. Now, the seagull problem, unfortunately, is not like the nicest of numbers, but we can look at the same sort of idea here when you have some sort of velocity of a person relative to the earth being equal to the velocity of, say, um, the person relative to train, and the velocity of the train relative to the earth. And if you're like, wait, what numbers go where? You can use simple numbers like just like 10 meters per second. So if you've got like a train that's moving, let's say in one direction, and you're also moving in that same direction, and you're going at 10 meters per second, you can kind of think about like, oh, that person's going to look like they're moving pretty quick. So you've got this like train or platform that's moving that way, and then on top of that there's this person who's moving that way with some sort of speed. Let's say it's the same speed, like so that we can just see the magnitudes there. Well, the resultant is going to be those two numbers put together, so it's just a combination of those two. So you can see that if we just have the train's moving at like a positive 10 meters per second, and you are moving at a positive 10 meters per second relative to that train, that relative to the ground, you would look like you're moving at 20 meters per second. So that would be like this first part, if they're moving in the same direction. If they're moving in opposite directions, they kind of cancel out. So it's the same sort of calculation, same sort of idea here, but slightly different. So if we're doing like this part B, if they're moving in opposite directions, then you're going to be imagining that either you're going in the negative direction or the train is going in the negative direction, one or the other, and these numbers, they cancel out. So if you're walking one way and the train's going the other way, someone looking at you from the ground might look like you're just still if you happen to cancel out. So that situation is how I like to think of these problems. Now, you're probably not going to have numbers that cancel out exactly here. Let's say that we've got the same sort of idea here, but you're walking not exactly at the same speed as the train. So let's say that maybe the train is moving at 10 meters per second and you're moving at 5. So the person relative to the train is 5 meters per second. Maybe you're walking in the same direction as that train. And in that case, you just kind of add those numbers up. And you can see that the ground, relative to the ground, it would look like you're going pretty quick. A little bit quicker than just 5 meters per second. It would look like 15 meters per second. Again, this should be if you're moving with the direction of the train. If you're going the opposite direction, you're just gonna look like you're moving 5 meters per second. But yeah, it just kind of works out to be that same speed with the numbers we did. So if you're not sure how to think about these problems, give yourself simple numbers like 5 or 10, and that can help you with getting an estimate of what goes where within the problem. Yes, you could subtract some numbers to get other parts of this, but I wouldn't really think about it that way, um, because usually this formula is written in this format. Sometimes they do it with the subtraction, which is weird to me. But you can see that there is the same sort of relationship if you're subtracting one part from the other. This problem is going to involve some small calculations, but they're not too bad. So we'll go ahead and go through that. So if we've got 19 minutes, then we can just convert that into seconds. Because we're working with meters per second, I'm thinking let's make this in meters and seconds for our units. So in 1 minute, you've got 60 seconds. So you just have your 19 times your 60, pretty straightforward. But if you're working with these problems, it is nice to have these things in units that work together for just simplicity's sake. And then 5.8 kilometers. In a kilometer, we've got 1,000 meters. You should know those basic calculations. And if you're struggling with how to set up conversions, I do have some videos on that as well. But if you're doing these types of problems, that's probably something that you already have down. So if we have that, now we can say like, if it takes them that far to go relative to the Earth, this is the bird relative to Earth vector, which is that distance over that time. So you want to make sure you're combining the correct numbers to get your velocities, and having good notation is really, really important. I'm trying to keep the color coordination with what we had earlier just to make it simple. So we've got 5.08, because it was only 2 sig figs. It really is only limited to like 5.1. They weren't asking for that meters per second, so I'm gonna keep on using like the 5.08 number. Just have a couple extra sig figs on that just in case. So they're asking for the velocity of the wind. So this is kind of like what I talked about earlier, where you can subtract parts of this equation to get the other parts. So if you've got the velocity of the bird relative to the Earth, that should be related to the velocity of the bird relative to the air, plus the velocity of the air relative to the Earth. Now you could do this as a subtraction problem. For me, it's easier to see these numbers as being added together. You know, it's same sort of deal with our problem, just how you're looking at it. So we've got about 5 being our final speed going over relative to the Earth. And we know that they're flying at a velocity of 11 relative to the air. So they're going at about 11 meters per second in the positive direction, same direction as the final direction here. And they're going actually straight into the wind here. So if the wind's going one way, they're going the other way. So maybe the wind is actually going the opposite direction here. So in this case, the wind is going one way, and their final speed is going the other way, but like not that much the other way. Which means that we've got this mystery number. If I were to think of this as 10 and 5, it's like, okay, well, I need to be going at like positive 15-ish to get those numbers to work out. So I've got 5.08. It looks like if I added the 11 to that, I should be getting our final speed. So this is going to be a positive 16.08 meters per second. It was limited to that ones place, so that would be our final answer. 16.1 meters per second in the positive direction is our velocity of the air relative to the Earth. So we can think about that as one part of this problem, um, where it's like, okay, I'm gonna have to like swim against stream. If the stream's going back 10, I've got to go forward 15 relative to the water for someone to see me going about 5. So that is why I like using those simple numbers. Um, and then let's say that they turn around for part B here. Now they still do have the same speed in the air, but they're working together. So you have to think about this a little bit differently than what we had before. These numbers are now going to be them working together with the air. So like these two vectors are going in the same direction. So let's say you're now going with the current. You're going to be going pretty quick. This is like 10 plus 15. That adds up to about 25-ish. So we've got that 16.08 plus 11. Now I'm getting, what is that, 27.08? Or 27.1 if we're using the reported number from part A, which is the convention with these types of problems. If you've reported one number out, you can use that as the actual number. So let's say that this is 27.1 meters per second, and then it's just a simple thing to find how long it takes to go that distance. So you've got this velocity now relative to the Earth. I'm gonna keep color coordinated on us. If we can. It'll let me. We got the 27.1 meters per second, which is equal to that distance over some sort of time. And you can do a little algebra and solve for that pretty easily. It looks like it's going to take about 214 seconds to do that. Or, sorry, limited to 2 sig figs, or 3 sig figs, yeah, it's actually going to be 3 sig figs with that 27.1. So 214 is actually our correct answer there. Yeah. So let me know if you've got any questions on how you can think through a problem like that. It's a little bit weird, especially with the conversions, but they're going to do that often too in these problems. So for two-dimensional, we are combining vectors in a similar way to what we did with one-dimensional. For example, on part A, we had what was orange and green. Those are being combined to give us the black. And you can see in a similar way, if we have the orange going in a certain direction and that green also going in a similar direction, they add up to give us a vector that's like where they kind of overlap or line up to get that same magnitude. So the same sort of thing applies for two-dimensional vectors. Now I have a whole video on different ways of combining two-dimensional vectors. If this is a little bit too much for you, I would suggest watching that and then coming back here. So if we have this swimmer, this is a classic physics problem where there's some sort of river that they're crossing, and that river is going to be flowing down at a certain rate. So let's say that there's a swimmer that's crossing. The swimmer can travel 5 meters per second. Now it could be going straight across if this was still water. And that's going to have a magnitude of 5 meters per second. Now, because this river is flowing, they're going to have to use some of their momentum, if you will, to kind of cancel out that flow of the river. So they're not going to move relative to the ground at 5 meters per second. So in this problem, we're going to have to, in moving water, direct ourselves upward a little bit. Because the river is flowing down at a certain rate, let's say that's 3 meters per second, maybe in the negative direction, that means that it's going to need to be combining its x and y components in a way that cancels out what we've got here. So if we have this blue line, its y component needs to cancel out the negative 3 meters per second so that its y component cancels that out. Like they've got the same magnitude. And when you do that, you're getting some sort of resultant that looks something like this. So the resultant is where these two are kind of, if you follow along and you start the second vector from where the first one ends and go along, that's one way of thinking about this. But for me, it's easiest to see this as a change in x and change in y, where like there's change in x plus another change in x is equal to the total change in x. So you can think of that as like vector A, vector B being put together to make vector C, or the total vector. You can do the same thing with the y's, and think of that as what we're doing here. Now, luckily for us in this first problem, there is only one of these where both components are really being added in one of the axes. So there isn't really a change in the x here for this problem, so that's going to be 0. So like the only time that we're really looking at vectors being combined is in the y, and these are equal and opposite. So whatever this is as a negative number, this was as a positive number to give us a value of 0. Like this final vector is going straight across. So to make that final vector go straight across, these things need to cancel out in their y components. In other words, if this river is going down 3 meters per second in the y component, that means that our y component for the swimmer needs to be 3 meters per second. So we can go back to this triangle here and think about the swimmer's y component as being a positive 3 meters per second, and this being 5 meters per second going that way. Now there's a couple different ways to solve this once we get to this point. You've got your a squared plus b squared equals c squared. You may recognize this as your 3, 4, 5 triangle as well. So that's one way of doing it. You can also get like the angle in here using sine, cosine, and tangent. Couple different options. I'm just gonna go with the a squared plus b squared is equal to c squared option here. And we can see that c is 5, so 5 squared is going to be equal to 3 squared plus a squared. And if you do that, it works out very nicely so that this a squared is equal to 16. In other words, a has to be equal to 4 meters per second. You can think of these as like meters squared over second squared if you want to think about what's going on with those units as well, due to those units being squared. And so we've got a x component of 4 meters per second and a distance that's relative to that as well. So we want to think about this now as 4 meters per second as a resultant vector. And if we know that speed and we know the distance, velocity being equal to the change in d, or distance, over change in t, we've got 20 meters over some sort of change in time, and this is 4 meters per second. There's other versions of this equation that you could do, but you can kind of see the math. This is going to work out as 5 seconds to travel all the way across. And we're going to limit this to 1 sig fig as well, due to this answer being limited to 1 sig fig. And it was a whole number. You could do this as 4.000 if you wanted to, but it's going to end up being 1 sig fig in our final answer. So that's how you do that first problem. That's a little bit more straightforward, two-dimensional vector combination. We are going to do a bit of a more challenging one, but this is probably not something you'd see in like a high school physics class. This is more like a college level problem. So for this part of the video, I made a kind of an error slash it still works. Normally west you set up not going to the right. You usually set up west going to the left. So this problem is in a sense a mirror image of how you would normally set it up, but that is totally fine. We can have west be going in the positive direction and east going in the negative direction. Coordinate systems can be set up in that way. We just need to be careful with that because when you combine them, you might get switched around in the middle of the problem. So in hindsight, if I were to do this problem again, I probably would set it up so west is actually going to the left and east is going to the right. But this works, so I'm going to keep it as is for the video. And yeah, it might be interesting for you to work through it in the way that makes more sense to you and to me to set up west going to the left and east going to the right and seeing how it's similar. It looks a bit different, but it's just the mirror image. In this problem, we have an airplane that has an airspeed of 254 meters per second, meaning if there's no wind, that is its speed. And if it's traveling in some air that's traveling as well, this is the speed of it. It's kind of like you walking on the train, if you will. So this is the velocity of the plane relative to the air. And there's also this jet stream. You could think of that as velocity of the jet stream relative to the Earth being 36 meters per second. So they also have directions given here. Let's try and get that mapped out. So we've got something going 5 degrees south of west. So if this is like west, it's just a little bit below that. So it's like pretty much going west, but not exactly west. And it's gonna have some sort of small angle in here of 5 degrees and a magnitude of 254 meters per second. In addition to that, we have this other vector that's going 15 degrees south of east. So if this is east, then 15 degrees south of east is a bit more of a steep slope than the 5 degrees. So something kind of like this. It's not perfectly to scale, but this gets across the main idea. So we've got some sort of 15 degrees and the magnitude of 36 meters per second. Now, 36 is a lot smaller of a number than 254. So to make this to scale, I'm going to shrink that down quite a bit. And that is going to be a nice approximate of our second vector there that we're trying to do. Now I can just look at this and tell you that this is going to be going as a resultant somewhere in this direction, and give you a rough idea that looks like maybe 200-ish miles or meters per second. But to actually get this calculated, we're going to need to look at the x and y components and actually break them down. So this first one, what we had in blue, we're going to need to break that down into its x and y components, kind of like what we were talking about above. You can think about what's going on in terms of just these x and y values and how they get put together. So there's some sort of change in x. Let's call it change in x1 and change in y1, and then we're going to have change in x2 and change in y2. When those get put together, they add up to this total change in y, change in x. Again, I have a whole video going over this, and you're going to need to be careful because there's some negative numbers coming into play here in terms of our coordinate system. So we'll just be a little bit careful with our math, and that should be okay. So in this problem, we've got that 5 degrees, which is relevant, and then we've got the 254 meters per second. And if we want to do this problem, we're going to need to be using sine and cosine. So, ka, toa. I always write that out when I'm doing these trig function problems. in this context, we have our hypotenuse, we have our opposite, and we have our adjacent. So to get the change in x1, that's going to be this guy right here. And then we got change in y1. So to get change in x1, we're going to be working with that over the hypotenuse, which is, it looks like the adjacent over hypotenuse. So that would be our cosine. So if we've got cosine of 5 degrees, and I would really recommend you draw this out. It's not always x and y being the cosine and the sine functions here, so you just need to be careful and not make that assumption. But we've got this change in x over 1, and then we've got a value of 254 meters per second. And in that case, I usually keep it formatted like this so that I can get the 5, the cosine. Yeah, it's basically 1, which sounds reasonable to me because it looks like this is nearly as long as the hypotenuse when we're looking at those values. So 0.996. And that, it looks like we need to multiply it by the 254. So the change in x1 is 253.03. It will get limited down to 3 sig figs, so I'm just going to mark that for now. It's not an actual number we're working with in terms of an answer, so we don't need to round just quite yet. And that looks like that's going to the right, so I'm going to have that be a positive 253.03 meters per second. While we're doing this, I'm going to also do my sine function, my sine theta, of 5 degrees being equal to the opposite over adjacent. And in this case, the opposite is my change in y1, and we can work with that. So if we have sine of 5 degrees, that would be equal to the change in y1 over the 254 meters per second. This should be a pretty small value if we're thinking about it. So if we do 5, yeah, that's a pretty small number, 0.087. Yeah, pretty small number when we multiply it by the 254. So I'm getting 22.137 meters per second, getting limited to like 3 sig figs again. In this case, though, with our drawing, it's going to be going down, so it's probably going to need to have a negative 22.137 to help us keep track of the direction of these vectors. So we've got the blue triangle kind of worked out. Now we're going to do the same thing with our red. And that 15 degrees. We've got SOHCAHTOA, which I'm just going to copy that. The nice thing about doing this digitally is that you can easily copy the stuff over. And in this case, let's just look at this. If we're doing our sine theta, that would be opposite over hypotenuse. And we had the hypotenuse given to us. The opposite is here. Adjacent is here. And this is my change in x2 and change in y2. All right, so change in y2 is going to be over some hypotenuse. So if we do sine of 15 degrees, that's going to be change in y2 over the 36 meters per second. Let's just have a look, see what that does when we do the calculation there. 15 degrees and the sine function is 0.2588. So this is going to be small, but it's not like absolutely tiny considering the 36 that we're multiplying by. Yeah, like 9 sounds about right. And if I look at my triangle, that sounds about right. So 9.317. But again, this should be like a negative number in our coordinate system, so we'll need to be careful with that. Then we've also got our cosine theta here which is going to be my adjacent over hypotenuse, which is going to be my change in x2 over the hypotenuse of this problem. So if we do cosine 15 degrees, that would be equal to the change in x2 over 36. And I'd say the most common mistake that I see with problems is if they're not color coding, you end up pulling out the wrong hypotenuse for these calculations, or you're just trying to like skip too many steps, essentially. Trying to do too much in your head. And if you can write it out, it's just so much easier. So this is 0.965. Yeah, so this number is going to be almost 36. And I mean, I think I made this angle a little bit too big in my model, so it is a pretty small angle, so that does kind of make sense to me. So for our change in x2 value, we're getting that as 34.77. Yeah, seems all right to me, given the 15 degrees that we're thinking about right there. So when we plug these together, again, be careful to put your x's and your y's in the correct spot. So the change in x here is a negative number. Negative, was that 34.77 for our x value. And then our change in y is also a negative value, so it's 9.317. And we can have a look, see at what these calculate out to for our change in x and change in y values. So we've got 253.03 minus 34.77. Okay, I'm getting 218.16 meters per second. And when we do the y's, we've got negative numbers. They're both negative, so I'm just going to add them up. So this is a negative 31.474 meters per second. So we have x and y components for this green line right now. It looks like for it going over 218.16, it goes down 31.474 meters per second, which sounds pretty appropriate given our original drawing. And then if we want to solve for this magnitude, we could just do an a squared plus b squared plus, or is equal to c squared. That's probably the easiest way of doing this. You could also get the angle in here, which we're gonna need anyways in a little bit, and use that to get the hypotenuse distance. But we've got that number squared. So if we've got the 31.474, we're squaring that, and then we're adding that to this other one. When we do the square of that, that's 989. And we are going to be limiting this down to, I think it's 2 degree or 2 sig figs. So if we just have like another extra 1 or 2 sig figs on here, that should cover us with plenty of accuracy for what we're working with. Let's go that 218 number. That's going to be pretty big. Square that. Yeah. 47593. That's definitely a pretty big number. So we add those together. Yep, that sounds about right. And then we square root that. I'm getting 220. Which is appropriate. It's a bit longer than those R legs, 220.4 meters per second. Having this as like the 48,000 number might help you double check your calculations. So that's just a piece of advice that I would give you. We are being limited to 2 sig figs, so this is a 220 meters per second as our final answer there. And then for the angle, you can pick any of your SOHCAHTOA functions here to work with to get that hypotenuse. It's not too bad of a calculation. So let's go ahead and just pick one. So if we have this angle in here, we could do like sine of that angle is equal to opposite over hypotenuse. We've just calculated the hypotenuse. You could also get this from the opposite and adjacent if you wanted to work with the exact numbers that were provided. That's totally okay. This isn't going to affect it too much, seeing how we're only doing 2 sig figs in the end. So our hypotenuse was 220 meters per second, and our opposite in this case is we're just going to use the magnitude of this because you could kind of flip this triangle and make it go up. So we've got 31.474 meters per second over the 220. And because they asked for the previous part, I'd feel comfortable using that as a actual number for this problem. So you just do a little calculation work. 31.474 divided by that 220. That gives you a number of 0.143. That's equal to our sine theta. So theta is going to be, we do like the inverse sine function of this. 8 degrees. So 8 degrees, 0.22, or if we're limiting it to the 2 sig figs, 8.2 degrees. Right in the here. So they asked for how south of west this is. This is actually south of west, so that works out for that problem as well. That's how you would do this problem. Again, you can use the tan function with the opposite and adjacent. That would give you the same degrees, or it should be at least very close. Go ahead and try that as an extension to see how you're doing with it. Thank you.